Drive selection for robots or any mechanism that has a non-linear relationship between its input and output is not straightforward. We saw in an earlier video that simple linear mechanical systems present few difficulties in motor and gearbox selection. Most supplier catalogues contain simple formula to help with motor sizing. These usually assume that there exists an invariant J-load or inertia that can be calculated. In fact, there probably is for systems like this one. However, if the mechanism has a non-linear relationship between its input and output, then the concept of reflected inertia becomes difficult. With work, we could write down a formula for the torque, but the reflected inertia becomes a set of linear coefficients in acceleration and velocity. Go a step further and introduce a second degree of freedom, as in a planar parallel robot, and whoops, everything looks very complicated. So, reflected inertia is a limited concept when applied to mechanical systems. As MD Pro generates torque profiles, everything gets much easier. We no longer need to worry about inertia, we just use the torque. So now consider the MadBot we put together over the last tutorials. The lower axis requires a linear drive. I think a ball screw would be suitable. I need to add a rack and pinion to the mechanism and then turn this into a screw. This is how. We now need some geometry on the base part to mount the rack pinion. So I put a line just to the left of the slide line and now add a part and join it to the left hand point of the line with a pin joint. Next, add the rack and pinion. It needs only two lines, one driving on the slider and one to be driven on a new pinion part that we have just added. The rack and pinion by default will be drawn. We need a ball screw, so as usual double click on the rack to get the property editor and change to a ball screw. The screw will be drawn on the slideway line and the pinion will now spin with a speed defined by the lead of the screw. You can edit the lead screw or pitch in the property editor. We are nearly ready to select a motor. Before we do this though, we must configure the power now to come from the pinion joint 3. This is the joint that drives the screw. Now select the screw motor in the graphic area by double clicking on the motor. The joint drive dialog will appear. First select a motor, then select the coupling. At present there are no entries in the database for couplings, so I made one up. They are effectively gearheads with a 1:1 ratio and an efficiency of 1. I select the coupling. Displayed is a torque speed curve for the MadBot in its current configuration. The motor parameters provide an area that should enclose all the torque speed points. In this case, just about all the points lie outside. This selection would fail to meet the design performance of the robot. Now we can begin to explore and find the optimum drive performance. An important point to understand is that the calculated torque displayed in the graphic area does not include the torque required to accelerate the motor rotor. The torque speed curve does include this torque, as you can see when I select a motor with a very heavy rotor. I can change most parameters in the model, like the machine speed, and see the effect on the torque speed curve immediately. Here I'm trying to reduce the blend curve curvature. This should reduce the acceleration of the load and torque. So I experiment very quickly and I can get quantitative feedback in the torque speed curve, at the same time experimenting with different drive options. This process can be repeated for the upper pin joint. So I hope you can see how to design and improve a mechanism in Mech Designer. The techniques I have shown here can be applied just as well with a single degree of freedom mechanism, with cam mechanisms, pretty much any mechanism.